Hello, friends. We are back today. I know that it is Thursday. Hopefully, you guys have had a chance to talk to either myself or Mr. Larson, and we've been able to decide a way for you to analyze your data. And we're now at the point where we're going to be generating some interpretations and using our quantitative data to make some statements. And we are going to back those statements up with data and proof that we have come up with. So let's go ahead and take a look at some examples, and we're going to talk about essentially, one, how do you back up your decision to either accept or reject your hypothesis with data? And then two, how do we find rooms for error within our experiments? Alrighty, so example number one. The hypothesis is that if farms have more land, they will have more cows, because farms with more land can maintain more cows and cows are more profitable. So what we did is we took our table that we originally had and we recognized, wow, there's data for land. And then we extracted the information about cows and the information about land into a separate table and then formed a scatter plot chart to analyze it. Yesterday, I believe Mr. Larson took you guys through how to look at correlations. So now we're looking at this chart and it's looking at land and cows. And I'm thinking to myself, I wonder how the R-squared value is. If you think back, R-squared value indicates the strength of the correlation. So I'm looking at an R-squared value of 0.009, which is extremely weak. If you think back to yesterday, you want your R-squared value to be at 1, and that is what tells you that you have a strong correlation. So based off of this, I know that my correlation between the amount of land and the number of cows per farms in Indiana is very, very weak. There's no correlation there. So when I look back at my hypothesis that states that if farms have more land, they will have more cows, I can say that based off of an R-squared value of 0.009, we reject the hypothesis that the amount of land that you have influences the number of cows that you have. And that's that. So if you guys have a t-squared test, if you're doing something like that, you might end up either accepting your hypothesis, you can say that, or you can say that you fail to reject your hypothesis. You can't necessarily say that your hypothesis is true in fact because you don't have the information to back that up. However, you can say that you're not going to reject it, so you fail to reject. Alrighty, so let's look at another example. Here I'm looking at the number of goats and cows. The hypothesis is that if a farm has both goats and cows, they're going to have more goats than cows because goats are easier to take care of. So obviously I have a very strong background in farming with these examples, and we see that here our trend line goes sort of negatively through, and we see that there's a R-squared value of 0.56 if we round up. So, and if we look at it, it's also indicating, right, that as the number of goats go up, the number of cows decrease, and as the number of goats go down, the number of cows increase. So I think that this, you could say there's a maybe moderate, because we're at the 0.5 value, there's a moderate chance that this hypothesis is true. So maybe you could again fail to reject based off of that. However, the next step is then thinking, what additional data, what additional information should we get? What additional experiments should we run? That's the next step, and that goes in your generating interpretation / your conclusion as you start thinking about how to take this test and make it meaningful and how to move it forward. The last thing for generating interpretations, though, is to look at this information and ask yourself, what am I missing? What information am I missing? And that is called sources of error. So oftentimes, almost every single experiment will have some sources of human error because we are imperfect, flawed beings. And so maybe for this example, the imperfect error could be in like the time of day that, or the dates that this information was collected. Maybe I looked at farm 1 in 2019 January and I'm looking at farm 5 in 2016 May. Maybe the source of error could be that I haven't looked at the cows' ages and their deaths and the births, and I haven't updated those over time. So sources of error, you're thinking about what are these numbers not telling you about the complete story. If I'm looking at CSA New Tech and I'm looking at GPA for males and females, then I'm keeping out a lot of those pieces of that story, like grade and information like that. So what is the flaw? What are the flaws in your experiment? And that's what we're looking at